Let's keep going with the test review and finish up chapter 17 here. So the next bullet here is telling us the steps on how to solve this type of problem. If you're asked to find the force on a charge, what do you do? Well, first of all, there's going to have to be more than one charge. So maybe there's 3 charges. And I'm not going to go over the whole example because you do have a test review problem where you can practice actually getting numbers, but I just want to give you a brief overview. So you've got 3 charges, for example. One of them is positive. Let's try this one again here. So this one's positive, this one's negative, and this one's negative. And let's say it asks for the force on this charge right here. So draw and label each force acting on this charge. We're asked about this charge. So these 2 charges would attract because they're opposites, so you draw a force this way. And let's say that this is Q1, so this would be force 1. And let's say this is Q2. And then these 2 charges repel, so you would draw a force this way, and let's call it F2. So that's what this first bullet is saying. Find the x and y components of each force. Well, actually, before you do that, you actually have to calculate what these forces are. And to do that, you're going to use this equation right here for electric force. Right, you plug in both charges in here, how far apart they are, Coulomb's constant, which is right up here, and that will give you the magnitude of the force. So you definitely want to find those magnitudes first, get those numbers, and then once you do that, then you find the x and y component of each force. So you separate the x and the y directions, and you say, okay, this F1 here, it has an x and a y component, and then this F2 has a x and a y component. And you actually find these using sines and cosines. So I'll let you review that, but just fill out everything and then add x and y components separately. So it's talking about once you find numbers for these, you would add them. This would give you the total force in the x direction. You would add all these. That would give you the total force in the y direction. And then the last step would be find the magnitude and direction of the net force. So once you have these 2 forces, let's say that your fx was a negative number, so fx would go this way. Let's say fy was a positive number, so fy would go this way. Then you need to find the magnitude and direction of the force. You need to find F. This is the net force. So you would use Pythagorean theorem to find F. And then so that would go like this, fx squared plus fy squared. And then you would find this angle here. That would be theta. And that would be the inverse tan of the y over the x components. I don't think that these 2 equations are, no, those 2 equations are not on the equation sheet, so those you do have to know from Physics 1. And for finding the electric field at a point, you're going to do the same thing that we just did for the force. The only difference is that you're finding the field at a point instead of the force on a charge. So let's say that I had this case here, and actually I'll make it a little different just so to give you another example, but let's say we have a charge here and a charge here and a charge here, why not? So plus, minus, plus. So now you'd be asked, okay, what's the field at a certain point? So maybe you're asked for the field right here at point P. So instead of drawing forces, you're going to draw fields from each charge. So the field due to a negative charge always points toward that charge. So there's a field this way. Let's say this is Q1, Q2, and Q3. So this would be E1 here. The field due to charge 1 at this point. Q2 produces a field going away from it, so going away from it would be this way, right? You can draw a straight line and say, okay, it's going away from it. And then Q3, it's going away from it, so it would be going to the right here. So that would be E3. So that's what you're doing. So it's very similar to this, but here you're looking at, are the charges like charges or opposite charges, and that tells you which way the force goes. Here you're looking at, was the charge producing the field, was it positive or negative? And that tells you which way the field goes at this point. Once you've done this, then the process is exactly the same as right here. You're going to find the x and y components of each field. So instead of writing f1x, you would write e1x and e2x, etc., e3x. And then you would do the same thing for the y direction, e1y, e2y, e3y. And you need to find all of those components using sines and cosines, and then add them up just like you did here, and then use the Pythagorean theorem to find the net field at that point. So you're going to have one of these two problems on the test. It'll be probably 5 or 6 parts. So you definitely want to practice it, look at the practice problems and the review problems. And as I mentioned in class, the way that I break up the problems, right, I'm not just going to have one problem that says, okay, what's the final answer, what's the net force, or what's the direction of that net force, right? What I would do is I would break it up to you. Maybe I would say, which way does F2 point? What is F1? What is F2? What is the X component, right, of F1? What is the Y component of F2, right? I can just ask you a bunch of questions that you would need to be able to answer in order to get to the final answer. And that way I can make a problem be worth 15 or 18 points. And just to finish up chapter 17 here, because I think here, oh yeah, we have just this little bit left here. So, properties of conductors in the equilibrium. So, this here is more memorization. If you understand what it says, then it's easier to memorize. So if you have a conductor in equilibrium, let's say it's a sphere, it's a metal sphere, and it's in equilibrium, then we're saying that there's no electric field inside. We're saying that if there's charge on here, whether it could be positive or negative, but it would be on the surface. And all points are at the same potential. So maybe all of these points would be 5 volts. They're all at the same potential. And then the electric field is perpendicular to the surface, so there's no field inside, but there is a field produced by these charges here, and it points perpendicular. And that's also how you know that this surface is an equipotential surface, because equipotential surfaces are always perpendicular to electric field lines. And then you're going to have more charge at sharp points. So here, if it's a sphere, the charge would be evenly distributed. But if you had a little point on this surface, then there would be more charges that pile up. So as long as you understand what these mean, then if I asked you a question, which of the following statements are properties of conductors in equilibrium, then you'd be able to answer the question. And just to finish up chapter 17, let's make sure that we've looked at all the equations here. So all of this here, we don't have to worry about. I did mention Gauss's law in class, but the coverage was so brief and we didn't get to do any examples that we're not going to have to worry about it for this test.